Let's work through a few slightly more advanced integration by part integrals. We will work through examples 6 through 9. So first of all, example 6. We have the integral of e to the square root of x dx. This is a rather interesting problem. We're going to start the problem actually by using u substitution. So forget about integration by parts just for a second, and let's try integration by substitution. I see the square root of x as an inner function here. So I'm going to choose u equals the square root of x. Now follow the steps for substitution. The derivative of the square root of x is 1/2 times x to the negative 1/2. I'm going to write it as 1 over 2 square root of x. That's the derivative of the square root. And now solve for dx. If we cross multiply, we obtain dx equals 2 square root of x du. Now we can substitute into our expression. We have the integral of e to the u. Dx becomes 2 square root of x du. Now, after using integration by substitution, we want to only have one variable name in the transformed integral. Here we have two. And at first this looks like a problem. However, notice that square root of x is just u. So I'm going to use our back substitution technique. I'll take out the 2, that's just a constant, and I have e to the u times the square root of x, but now I'm writing that as u. We have 2 times the integral of e to the u times u. We will solve this using integration by parts. And since we already have a u in this expression, and we use the variable name u for integration by parts, this could be confusing. So let's just rename the variable to be something else. Let's use w. E to the w times w dw. And w is just the name that we're replacing for u. So w also equals square root of x. Let's just note that here. W equals square root of x. At the very end of the problem, we want to write the entire problem back in terms of x. All right, now this is actually the same example as example 1. We'll work through it again, but we worked through the same integral for example 1 on this handout. We apply integration by parts, choosing u to be w, and dv is everything remaining, e to the w dw. We find the derivative of u, this is dw, the integral of v, just e to the w, and now apply ultraviolet voodoo. We have 2 times u v minus the integral of v du, which is just dw. This becomes w times e to the w minus e to the w, and our final step is to replace w with the square root of x. We obtain 2 times square root of x, e raised to the square root of x, minus e raised to the square root of x, plus c, and there is our final answer. We used integration by substitution first, and then integration by parts. Once again, this is not uncommon to see multiple integration techniques in order to solve a single integral problem. Let's take a look at example 7. We have the integral of sine of x times cosine of x. I'm going to show you 2 different methods for solving this. The first method is probably the better one. It uses integration by substitution. But we can also solve this using integration by parts. So using u substitution, I will choose u equals sine of x. The derivative of sine is cosine. Solve now for dx. And now we can make the substitution into the integral. Once again, we are using u substitution here. We're not doing integration by parts. We'll do that as the second solution. So our integral becomes the integral of sine, that's u, times cosine, and dx turns into du divided by cosine of x. The cosines conveniently cancel, and we have the integral of u du. That is simply u squared divided by 2. U was sine, so this is sine squared of x divided by 2 plus c. That's one way to solve this problem, using u substitution. Let's take a look at a second solution where we'll use integration by parts. We need to choose part of the integrand to be u, and the rest is dv. Well, let's choose u equals sine, and dv equals cosine of x dx. Now, let's pause just for a second. This can be slightly confusing. We're using the same expression for u in u substitution and integration by parts. Remember, this is just the same variable name. The u concept for integration by parts and u substitution is completely different. It's merely a coincidence that we have the same expression for u here. We generally want to regard u in different ways for integration by parts versus integration by substitution. All right, let's continue with integration by parts. We find the derivative of sine, which is cosine. Integrate cosine to find v. The integral of cosine is sine. And now we can use ultraviolet voodoo. We have u times v minus the integral of v du. Now, take a look at what happened. This is quite interesting. After applying the integration by parts formula, our integral on the right-hand side of the equation matches the integral that we started with on the left. This looks rather strange. It seems almost as though we're going in circles. We have the same integral that we started with, so how do we continue with the problem? Well, this is a very cool trick that sometimes happens in integration by parts when we obtain the same integral after applying the integration by parts formula. Watch what we can do. I'm going to add this integral to both sides of the equation. I simply add the integral of sine times cosine. On the right-hand side, I'm adding and subtracting the same quantity, so those cancel. On the left, I'm adding the same integral to itself. So this becomes 2 times the integral of sine of x, cosine of x. This is my starting integral. This is the problem that I started with. And this equals sine times sine, which is sine squared of x. Now to solve the integral, I simply divide both sides by 2, and I have my solution. Add a plus c, and look what we have. The integral of sine times cosine is sine squared of x divided by 2 plus c, which is exactly what we got when we used u substitution. Let's take a look at problem 8. Problem 8, in my opinion, is a fairly advanced integration by parts example. We have the integral of 2x cubed times cosine of x squared plus 4 dx. We're going to solve this using integration by parts. And the way to choose u here is not very straightforward. I see an algebraic function 2x cubed, and if I follow the LIATE rule, I would probably choose this to be u. We could start that and attempt the problem, and we would realize that that does not work out. So before we start integration by parts, I'm going to rewrite this integral. I will write it as x squared times 2x times cosine of x squared plus 4 dx. This seems a little bit arbitrary, but focus on these second two factors, 2x times cosine of x squared plus 4. Notice that the derivative of x squared plus 4 is 2x. We are going to choose this expression for dv, and we will use substitution to evaluate that integral. Here's what happens. I apply integration by parts. I will choose u equals x squared. dv is everything that's left over. 2x cosine of x squared plus 4 dx. Finding du is easy. It's the derivative of 2x, the derivative of x squared, so 2x dx. V is the integral of dv, so I need to integrate 2x cosine of x squared plus 4 dx. Let's handle this integral off to the side separately. In order to solve this, I will choose u substitution, and I'm going to choose u to be the inner function x squared plus 4. Once again, the u that I'm using for u substitution is different from the u that I used in integration by parts. It's unfortunate that we use the same variable name, but we don't want to get those confused. Take the derivative of this u, it's 2x, and now substitute back into the integral. We have the integral of 2x cosine of u dx. Oh, we forgot to solve for that. dx here is du divided by 2x. So dx in the integral becomes du divided by 2x. The 2x's cancel, and we're integrating cosine of u. Antiderivative of cosine is sine, and instead of writing sine of u, I'm going to replace the u with x squared plus 4. That was pretty involved. That's just the first step for the integration by parts on this problem. But we found that v, after using an integration by substitution, we found that v equals sine of x squared plus 4. And if we think through checking this, if you take the derivative of sine of x squared plus 4, using the chain rule, you'll get 2x times cosine of x squared plus 4. Now that we have this, let's apply the integration by parts formula. We want u, which is x squared, times v, sine of x squared plus 4, minus the integral of v, sine of x squared plus 4, du, 2x dx. This is the original integral. We still have to evaluate this final integral, and this should look familiar. This looks very close to the integral that we just evaluated for dv. We'll actually skip some of the steps here, but if we work through this, we'd really do a u substitution here. For this, we would choose u equals x squared plus 4, and we could work through all the steps, but in the end, here's our final answer. Antiderivative of sine is negative cosine. I already have a negative here, so I have negative, negative, positive cosine of x squared plus 4. If we wanted to, we could double check that this is the correct antiderivative, add a plus c, and that is the final answer. Let's take a look at one more example. Example 9 is the integral of e to the x cosine of 2x dx. We will solve this using integration by parts. We need to choose what value to pick for u. And if we follow our acronym, there's no logarithmic function, there's no inverse trig, there's no algebraic function. The next option is trigonometric. So we will choose u equals cosine of 2x. dv is everything that's left, e to the x dx. So now follow the steps of integration by parts, find the derivative. It's negative sine of 2x times the derivative of 2x, which is 2. Antiderivative of e to the x is e to the x. Now apply the ultraviolet voodoo formula. u v minus the integral of v du. All right, I have a negative and a negative here. I can just make those both positives. Negative times a negative. And there's the 2 inside the integral that I want to remove to the outside. So I'll take one step to simplify. cosine of 2x e to the x plus 2 times the integral of e to the x sine of 2x dx. All right, after applying integration by parts, we have a very similar integral to the one that we started with. We've just replaced the cosine with a sine. So what can we do? Well, we'll try integration by parts again. Once again, I will choose u to be the trigonometric function, which is now sine of 2x. dv is e to the x. Derivative of sine of 2x is 2 cosine of 2x, applying the chain rule. Antiderivative of e to the x is e to the x. I noticed after the fact that I forgot to write dx in 3 places, which is sloppy of me. There should be a dx here, there should be a dx here, and there should be a dx here. It's rather minor, but I should not have used sloppy notation there. All right, back to the problem. So let's bring this down. This is cosine of 2x e to the x. I'm just copying that from the step above. And now I apply the integration by parts formula. I have 2 times, now I need uv minus the integral of v du for these new choices. U is sine of 2x, v e to the x, minus the integral of v du, 2 cosine 2x dx. All of this is equal to the original integral. And notice that our new integral at this step that we're at is actually the same as what we started with. We just have a times 2 in here. Other than that, it's the same integral. This is one of those problems where we can move this expression for the integral to the other side, and we'll be able to solve the integral that way. So all of this is equal to the original problem, which was the integral of e to the x cosine of 2x dx. All right, let's simplify. Bringing this down, we have the integral of e to the x cosine x dx. And there's a lot of stuff here to copy down. Cosine of 2x e to the x. I'm going to distribute the 2. So 2 times sine of 2x e to the x. And now I'll take this 2 in this integral, bring it out front. So there's a multiple of 2 out front. 2 times that multiple of 2 gives me a minus 4 times the integral of e to the x cosine of 2x. I will move this minus 4 to the other side, or we could think of adding 4 times the integral to both sides. On the left-hand side, I will have 5, 1 plus 4, 5 times the integral of e to the x cosine of 2x. On the other side, I simply copy down what I had before. Cosine of 2x e to the x plus 2 sine of 2x e to the x. And now this integral is where we started. That's the integral that we're trying to evaluate. And if I simply divide both sides by 5, I can find the value. So divide by 5, add plus c. This is our final answer. To think of u as a different sort of a thing for we generally want to think of u as a different sort of